Okay, so now that we've gone through all the transformations, we're going to finally put them all together in one form. And it turns out that in this one form we can find some very accurate information, and graphing can be made pretty easy. So for starters, let me just start by telling you what the standard form is. So f of x equals a, x minus h, that quantity squared, plus k. It turns out that all quadratics can be put in this form. Okay, so that's going to be a challenge because we've seen earlier, right, when we started this, we said that that was always the form. This is what we call the general form. And it does turn out that these two, we can go back and forth. So that's going to be 11.7. But using what we know right now, right, we can basically transform, right? We're transforming the graph of y equals x squared. So what's the h going to do? Well, the h is going to shift us left or right depending if we're adding or subtracting, right? What's the k going to do? The k, right? So that's what h is going to do. What's the k going to do? It's going to move us up or down, right? And then this a is pretty important because if a is going to tell us, are we going to get skinny or are we going to get compressed, right? So are we going to stretch or are we going to compress? And then if a is less than 0, if it's negative, that means we're actually going to even go down. So all the things, all the transformations we talked about, transforming left or right, shifting up or down, right, stretching or compressing or flipping through the x-axis, they're all located in this form. So we have all our bases covered. So we can manipulate x squared by that form. So that's basically where they're all at. And so, you know, looking at some examples, let's say we have f of x equals 2, x minus 2, plus 2, right? So put a bunch of 2's there. So what this is basically telling me, if we look at each piece alone, right, it looks, let me write the formula above, right? What this is telling us is that a is equal to 2. We have x minus 2, so h is equal to 2, right? Because h is in a subtraction statement, and then we're adding k, so k is equal to 2. So what this basically tells us is that our vertex is going to be at the point 2, 2. Right? So since h is 2, that means we're subtracting 2, that means we're actually moving to the right 2 paces. K tells us we're moving up 2 places, and this 2 right here says that we're going to be a little skinny. We're going to be a stretch. And so without point plotting anything, which we'll do here in a moment, I know my vertex has now moved over to 2 over 2, and the graph's going to be a little bit skinnier than our normal graph is. Now you guys know I usually like more accuracy than that. I usually ask for 3 points, and I'll talk momentarily about how we're going to find those 3, because right now all we have is 1, just based off of the formula that I have here. Doing another example, if we had f of x equals, let's say 3, x plus 3 squared minus 3. All right, again, we're going to have to be careful. We're trying to match this form. And we can kind of see we're off by signs. What's really clear is a is equal to 3. Here we've learned that this actually shifts us to the left 3 units, and this minus 3 actually shifts us down 3 units. But in terms of the formula, we're still consistent, because x minus h, we can rewrite that as x minus negative 3, right? And so we can see that h is negative 3, or it matches the shift to the left. Here we can rewrite this part as plus negative 3. And so that tells us that k is negative 3 to match the shifting of the down. So again, the formula itself, we have a subtraction statement within the parentheses. We either have it like I did here and we can just read it accurately, or we can rewrite it as a subtraction statement, or you just memorize what it meant to shift, right? When we were subtracting, we moved right. When we were adding, we were moving left. And then out here, the plus k, right? What that plus k did is we moved up or down, right? If it was already addition, we moved up. If it's subtraction, we move down, and that's the reason why, because it's the same thing as adding a negative or subtracting a negative in that case. So in this case, we have a vertex that's sitting at negative 3, and that 3 says we're real skinny. So if I was just doing a real quick point plot, I'd go to negative 3, and then I'd make my graph even skinnier than this one, since we're stretching by 3 rather than that. Again, I'm going to be asking for more accuracy than that, but there's a really quick sketch. And like I said, the payoff to this is because it's in such a nice form, we can draw a nice sketch. I can now start talking about my range, right? In this case, the range would be from 2 to infinity, and over here the range would be from -3 to infinity. So I can find the range really fast. I could also see that, this guy right here doesn't have any x-intercepts. So if we were to set this equal to 0, I'd get complex solutions. Over here, visually, I can see I am crossing the x-axis twice. So if I was to set this equal to 0, I'd have 2 real solutions. So you can really quickly, by just picking out the information and sketching a real quick sketch, we already have a lot of information about our function. So it's a very nice form to use. So there's how we're going to put all these transformations together in this standard form. Let's go practice it, and like I said, what I'll do is tell you how exactly we're going to get the 3 points I want you to graph, because we're going to take total advantage of the fact that we're symmetric, and we'll see that in the next video. But there's how we put it all together in standard form.